When you click something on the internet, you just kind of assume there's a server somewhere that has your data. It just sends it back to you, right? Like water coming out of a tap, you don't think about the pipes, it just works. That's actually pretty reasonable way to think about it, except when you are running something at a scale of Amazon or Google. That mental model completely falls apart. And today, we are going to look at exactly why it falls apart and the algorithm that fixes it. It's called consistent hashing. I promise it's way more interesting than the name sounds. But before we get into, if you are new here, I am Harshita Gadhuria, Associate Software Engineer at ServiceNow. On this channel, we go past the surface level stuff into the actual engineering behind AI and scalable systems, real problems, real failures, and the fixes that most people never see until something breaks in production. This video is part of my deep dive system design series. Chapter 1 was all about rate limiters, how Cloudflare handles insane amounts of traffic, the algorithms behind it. I have linked it with the I button up. You can watch it. That before or after, it's totally up to you. But if you want the full picture, I would suggest starting there first. And just so you know, this channel isn't only system design. I also run a decoding AI series where I break down LLMs, agents, workflows, chainings in the simplest way I can. If this sounds something you would enjoy, links are pinned for you. Okay, let's get into it. So, consistent hashing. The reason this matters is simple. It's the thing that stops your servers from completely collapsing the moment you try to scale them. Your chat messages, your video streams, your shopping cart, all of that lives on a physical server somewhere. And there's very specific mathematical trick that makes sure requests find the right server even when those servers are constantly failing, restarting, and getting replaced. To understand it properly, we are going to pull from three real industry papers: Amazon's Dynamo paper from 2007, Google's Maglev paper from 2016, and Apache system design document. These aren't just theory, these are actual system handling your data right now. Let's start with the problem. Before we look at the elegant solution, we have to isolate the actual problem. You already understand horizontal scaling, right? Okay, let's give me a short explanation. One server can't handle the load. You spin up thousands of commodity servers, slap a load balancer in front, then distribute the traffic to those load balancers. Easy? But nightmare scenario isn't routing stateless web data. It's stateful data. That's cache and databases. If you have 10,000 servers, so how do we calculate that this request is routing to which server? So, from so long, we are using a mechanism, we can say a formula, to calculate server indexes. Like we do use this one, hash key modulo n, to calculate a server index, where this n is particularly the total number of servers, total number of cache servers or database servers where we are going to retrieve the request, route a request to or retrieve the data from. Okay, so you might take a user ID and push it through SHA 256 or MD5. You got a massive integer, a huge random looking number. Suppose we have 100 cache servers. You divide that number by 100 and take the remainder. Now this remainder always lie between 0 to 99, right? And this remainder is your server index. And thus it maps perfectly to your 100 servers. In massive data center, n is never static. Okay, we have mapped our request to our servers. It's fine. User IDs, users request to servers, but servers fail every single day. Traffic spikes require auto scaling new nodes constantly. Let's take your 100 cache servers, model your denominator 100. But Black Friday hits, we need to add one more server. Load balancer automatically spins up one new server to help. Now our n becomes 101. From that 100, now 101. And all keys need a remap because are all of the keys associate to all the calculations depending upon 100. And now its n is 101. We are going to divide by 101. And this arithmetic consequences would be hard for us to handle. Basically, you divide the same integer by 101 instead of 100, the remainder changes, not just for the new data, for almost every single piece of existing data in your entire system. A key that used to map to server 42 now maps to server 87 might be, or anything else. Everything shifts. You experience instantaneous system-wide cache miss, which would be hard to handle because it's going to route our database for further queries, because if data is not into that server, our server is going to touch our database and trying to get the results out of it, which will cause DB thundering horde problem. The database gets the hit with a million of unexpected reads in fraction of seconds. It locks up, connections time out, cache servers crash waiting for the responses. Your application goes dark because you added one server to help with the load. Think of it like a musical chairs. 100 people, 100 chairs, everyone is seated. You add just one chair or remove one. The music stops, every single person in the room just scrambles for completely different seat. Absolute chaos. We are here at the solution, the consistent hashing algorithm. In 1997, it was invented, and the conceptual leap was this, that we should abandon the array because instead of mapping the data to list constrained by the number of servers, consistent hash mapping usually helps you maps both the data and the servers on the fixed circular ring integer space. Like you can see here, there are servers and data. This is the user data requested for, and the data and servers are plotted on that hash ring. And we use a hash function that outputs an integer between 0 to 2 raised to power 32 minus 1. We conceptualize that range as a circle where we maximize the value wraps back around to 0. See, there are it's a two-step process of the placements of data and server. Obviously, what will we do? We'll hash your servers. We'll take IP address of server. Okay, we'll take IP address of server and then we'll hash it, run it through a hash function. Resulting integer determines where the physical machine sits on the screen. Like here in this case, it's on somewhat 50,000 position. Okay, so server A might sit at 10,000, B at 50, C at somewhere 200,000. So now route the data when user requests a photo. For example, the user requested a photo. You hash the photo's ID to get its position on the ring. And then you apply one simple spatial rule. Walk clockwise until you hit a server. That servers own your data. Server A will go down, for example. Then all the traffic routing to B would be going to server C, obviously. Right? We'll go into the clockwise direction. Look for nearest server, the nearest servers we have in that direction. And we'll go for that. And crucially, if data is routing for server A, server D, server Z, any of these, we don't even care about it. We just need to route that data to the closest one in that clockwise direction. That's it. So for one line conclusion, if we can say key insight, if a node added or removed, a neighbor partition moves, all other keys unaffected. All of the hierarchy sits in place. We just go for the next possible server in that direction, clockwise, right? And if we go further, and naive hashing is a game of, for example, a musical chair. And a consistent hashing is a group of people sitting on the floor in a massive circle. If one person stands up and leaves, they don't force everyone to move. They just tap the person to their immediate left and say, "Hey, cover my spot." The rest of the circle doesn't even notice. And this is the solution to solve this bigger problem. In consistent hashing, we have seen the hash ring, that spatial mapping is elegant on a whiteboard, but how does the CPU actually execute a walk clockwise? Because a CPU doesn't have a finger to trace on a circle. If you have thousands of servers pointing on this ring and checking each one literally to find the next highest number, is of an operation, way too slow for real-time network routing. You could keep a sorted array and use a binary search of Logan lookups fast enough, right? But don't you think inserting into a massive sorted array when a server joins or leaves, that's an of n insertion penalty? You have to shift thousands of elements in memory every time the cluster changes. And production systems do not use arrays. They use self-balancing binary search trees, which are commonly used as red-black trees. Here's how it works in memory. Every node in a tree has a color, either red or black. So mathematical rules govern how nodes connect, and those rules are designed to prevent the tree from becoming lopsided. When you add or remove a server, the tree inserts a node and then performs a series of color flips and structural rotations. It rebalances itself and guarantees that the path from the root to the furthest leaf is no more twice as long as to the nearest leaf, which means the search. Is the server I'm looking for greater or less than this node? Constantly cuts the search space into half, which guarantees of log n for lookups, insertions, and deletions. As the cluster scales, the tree stays balanced, the ring stays fast. But the red-black tree solves the problem of speed lookup. It doesn't solve the geometry problem because hash functions are pseudo-random. If you have four servers, there is absolutely zero mathematical guarantee that they'll space themselves evenly. They could all randomly cluster together, and if they cluster, for example, server A might be end up responsible for 80% of the integer space, while server B, C, D split the remaining 20%. Server A's hardware buckles under load, and the other sits idle. It's even more severe version of the problem. That's hotspot key problem. Even the servers space themselves perfectly, data isn't accessed uniformly. Imagine Twitter's infra. Most accounts get maybe a dozens of requests a day, but if the cache keys for Justin Bieber or Lady Gaga all probabilistically hash to the same spatial partition on the ring, the read requests for that shard measured in millions per second. The machine backing that partition fails instantly. The ring reroutes to the next clockwise server. The server fails too. Cascading collapse, total system failure. Server A doesn't own one massive contiguous slice anymore. It owns 256 microscopic slots scattered evenly around the circle, which instantly solves the celebrity problem. Lady Gaga and Justin Bieber might hash to different slots. And since server A's slots are interleaved with server B's slots, those hotspots are almost certainly handled by completely different physical hardware. This load smears itself perfectly. Now, you might be thinking, we said the ring uses red black tree. Now, if we have 1000 nodes and 256 virtual nodes each, we just plotted our search tree and we just make our 1000 entries to 250,000 entries. Doesn't that destroy CPU cache locality and slow down routing? Let's look at the actual math. The base 2 logarithm of 1000 is 10. And finding a server takes at most 10 hops through the tree. The base 2 logarithm of 250,000 is about 18. You increased the tree size by a factor of 250 but added only 8 computational steps. And modern CPUs can traverse 8 memory pointers in nanoseconds. The trade-off is mathematically flawless. An insignificant increase in lookup time complexity eliminates structural load imbalances. As this topic is a bit lengthy, it wouldn't be good to squeeze everything into one video. So I am breaking it down into two parts and I'll be covering the rest of the five section into the next part. So stay tuned. So that's it for the video. If you stay till this point, I hope you understand some things better than you did before. And if you genuinely like this video, make sure to hit the like button and subscribe to the channel to follow me along in this series. See you in the next video. Till then, bye bye.